Picture a world so warm, so different from our own, that it almost feels like science fiction 50 million years ago. Our planet was a global hothouse, a world without ice, palm trees swayed in humid breezes, and crocodiles lazed in swampy rivers, not in the tropics, but near the North Pole. That is not our world. Our planet, the one you're on right now, is an icehouse, defined by the colossal sheets of ice smothering Greenland and Antarctica. A world of polar bears and penguins, of frozen tundra and seasonal blizzards. The change is so profound, it's like someone found the planet's master thermostat and deliberately turned it all the way down. That shift, from a sweltering greenhouse to a planetary freezer, is one of the greatest climate mysteries in Earth's history.
What happened?
What could possibly flip a switch on a global scale and send the entire world into a deep freeze that has lasted for millions of years? That is the puzzle we are going to solve. If you're using these to fall asleep, that's literally why I make them, so subscribe maybe, and tell me, where are you, and what time? I check the comments, and it's like Sydney at sunrise, Seattle in the dead of night, all listening at once. So to solve the mystery of how Earth got cold, we first have to understand just how impossibly hot it really was. Let's zero in on that greenhouse world. We are in the early Eocene epoch, around 49 million years ago. The key to this world is in the air itself. Atmospheric carbon dioxide levels were staggering, hovering at over 1,000 parts per million. For context, before we started burning fossil fuels, our planet's CO2 level was a comfortable 280. Today, with all of our climate anxiety, we've pushed it to around 420. The Eocene world was more than double. Even that, it was a planet wrapped in a thick, heat-trapping blanket of its own making. The thermostat was cranked to the absolute maximum. But the heat wasn't the only thing that made this world so alien. The very map of the planet was wrong. North America and Eurasia were shifted, closer together, almost pinching off the top of the world. The result was a piece of geography so strange, it's hard to even imagine. The Arctic Ocean was almost completely landlocked, a vast polar sea with only a few narrow, shallow seaways connecting it to the great global oceans. Think of it like a giant pot of water on a global stove, but with the lid kept firmly on. There was no deep, cold current flowing in from the Atlantic or Pacific to stir things up and cool it down. There was no global circulation. It just sat there, stagnant and isolated, collecting rainwater and river runoff, growing warmer and stranger with each passing millennium. This bizarre, forgotten geography is more than just a historical curiosity. It is the scene of the crime, and it's here, in this strange, isolated ocean, that the first clues to our planet's great cooling were waiting to be found. So, how do you investigate a crime that happened nearly 50 million years ago at the bottom of a now vanished sea? You can't send a detective, you send a drill bit. You go looking for the evidence, which in geology is buried in layers of mud. Think of the ocean floor as a history book, with each new layer of sediment being a new page laid on top of the old ones. For decades, scientific drilling ships have been plumbing the depths of the modern Arctic, punching through the seafloor to pull up long cylindrical cores of this ancient history. Mile after mile of mud, pulled up onto the deck, meticulously labeled, and sent to labs around the world. For the most part, these cores told a story. Geologists expected layer after layer of fine-grained mud, the slow, patient accumulation of deep time. But as they drilled deeper, back to the age of the great hothouse, they found something that didn't belong. A single, stark, jet-black layer. It was strange, thick and dense. It stood out like a smear of tar, pressed between the lighter-colored pages of Earth's memory. It wasn't volcanic ash. It wasn't normal sediment. It was something else entirely. Geologists simply called it the black mat. But the truly mind-bending discovery came when they dated it. This mysterious black mat appeared in the geological record at precisely the moment the Earth's long, slow cooling began. It was the geological equivalent of finding a suspect's fingerprint right on the murder weapon. The timing was perfect. Too perfect. There was just one massive problem. They had a clue, but the clue itself was a puzzle. They had no idea what this black mat was. or how a layer of pure organic ooze could form across the entire floor of the Arctic Ocean. They had found the first piece of evidence in the great climate mystery, and it only made the puzzle deeper. That mysterious black mat was the ultimate clue. It was a geological smoking gun. But a clue isn't a solution. To understand what it was, and what it did, scientists needed a better sample, a perfect, undisturbed record of that ancient, isolated Arctic Ocean. They needed to find the one place on the planet that had been collecting sediment, layer by layer, without interruption for 50 million years. And they knew exactly where to look. Deep beneath the permanent ice of the North Pole lies a colossal, submerged mountain range called the Lomonosov Ridge. It's an enormous slab of continental crust that ripped away from Siberia millions of years ago, and it slices the Arctic basin nearly in two. Think of it as a submerged spine running across the top of the world. For geologists, this ridge was the Holy Grail. It was far from any land, meaning the sediment there would be purely marine, a clean signal. It was high enough that it had been protected from the scouring of deep ocean currents. It was the perfect history book. There was just one problem, a massive, planet-sized problem. It was located almost precisely at the North Pole, covered year-round by a thick, violent, and constantly moving sheet of sea ice. Trying to drill a core sample there is an almost incomprehensibly difficult task. A normal scientific drilling ship would be crushed to pieces in days. The ship has to stay perfectly still over a single spot for weeks, lowering a thin drill string through over 1,000 meters of water. But the ice at the North Pole is not a solid, stable sheet. It's a chaotic mosaic of massive ice flows, some the size of cities, all grinding against each other, pushed around by wind and current. It's like trying to thread a needle from a helicopter while flying through a demolition derby. It had never been done. Many said it couldn't be done. But the answer to one of Earth's greatest climate mysteries was waiting down there. And so, in 2004, an international team of scientists decided to do the impossible. They launched one of the most audacious scientific missions ever attempted, the Arctic Coring Expedition, or ACX. Their plan was pure, brute force genius. They assembled a small armada. One ship, the drill ship, would hold its position over the Lomonosov Ridge, its engines struggling constantly against the ice. And flanking it, like two colossal bodyguards, were two of the most powerful icebreakers ever built. Their only job was to run interference. They would circle the drill ship constantly, identifying and shattering the enormous ice flows that threatened the mission, clearing a path, buying the scientists precious time. For 35 days, this ballet of steel and ice played out at the top of the world. The icebreakers battled the grinding polar pack, while the drill ship bored deeper and deeper into the seafloor, further back into time. And finally, they hit their target. They pulled up the first ever sediment cores from the heart of the Eocene Arctic Ocean. These cores were the prize, the complete, unbroken story of what happened 50 million years ago, pulled from the bottom of the world. And as they sliced them open, they realized the story they told was far stranger and far more profound than anyone had ever imagined. So there they were, these precious cores from the top of the world, split open on lab tables, and in them, that same mysterious fingerprint seen in earlier, messier samples, the black mat, a stark dark line drawn across geological time, right when the planet began to freeze. But now they had a perfect, high-resolution copy. They could finally put the clue under the microscope. Scientists took a tiny, almost infinitesimal fleck of the black mat. They prepared it, slid it under a lens, and peered into an ancient world. They were expecting to see mineral grains, the fine-grained silt and clay that make up normal ocean sediment. That is not what they saw. It wasn't mud. It wasn't volcanic ash. It wasn't the slow, patient dust of a dead seabed. It was something else entirely. It was life, or rather the ghosts of it. Under the microscope, the black mat revealed its true nature. It wasn't a solid mass. It was a layer of countless microscopic, individual bodies, all packed together so tightly they had become one, not thousands, not millions, but billions upon billions of them, compressed into a single, dense layer of pure organic matter. They were spores, the fossilized spores of a single type of plant. And when paleontologists identified it, the mystery only deepened. The culprit wasn't some exotic deep-sea microbe. It was a tiny, humble, almost comically simple freshwater fern. Its name is Azolla. Suddenly, the pieces all clicked into place with a terrifying, mind-bending clarity. That mysterious layer of black ooze covering the bottom of the ancient Arctic Ocean wasn't mud. It was a graveyard. It was the remains of a single, continuous, planetary-scale bloom of this one tiny fern for hundreds of thousands of years. Generation after generation of Azolla had bloomed, died, and rained down onto the seafloor, forming a blanket of dead life hundreds of miles wide. The black mat was the tombstone for the largest plant bloom the world has ever known. But this incredible revelation didn't solve the puzzle. It just changed it into something far bigger, far more profound. They had answered the what, but the answer made the how and the why almost incomprehensible. How could a freshwater fern, a plant that dies instantly in saltwater, grow in a massive bloom that covered the surface of an entire ocean? And more importantly, how could a simple floating plant possibly be the trigger for flipping the Earth's thermostat from a global hothouse into a permanent ice age? So, we have our culprit, a humble, microscopic freshwater fern, and we have the scale of its impact, a bloom so enormous it carpeted an entire ocean and left a tombstone of organic matter at the bottom of the world. But that just raises an even more fundamental question. How does a simple plant achieve something on a geological scale? Plants need nutrients to grow: nitrogen, phosphorus, the basic building blocks of life. An ocean-sized bloom would require a truly staggering amount of fertilizer, far more than the isolated Arctic Ocean could possibly have provided. To understand what happened, you have to realize that Azolla isn't just a plant, it's a biological machine. It harbors a secret weapon, a kind of superpower that makes it one of the fastest-growing organisms on the planet. If you were to peek inside one of its tiny frilly leaves, you'd find a small, hidden cavity, and inside that cavity lives a secret partner, a species of cyanobacterium with a single profound talent. This bacterium can do something most life on Earth cannot. It can pull nitrogen gas directly out of the atmosphere and convert it into usable fertilizer for the fern. It's one of the most powerful symbiotic relationships ever evolved. Think of it like a car that makes its own fuel, or a factory that produces its own raw materials. Azolla isn't limited by the nutrients in the water around it. It brings its own all-you-can-eat, infinite fertilizer supply with it, everywhere it goes. And because of this, its growth rate is almost incomprehensible. Under ideal conditions, a patch of Azolla can double its mass every 2 to 3 days. That's not a typo. It's the terrifying, relentless power of exponential growth. One plant becomes 2, 2 become 4, 4 become 8. A single tiny fern could cover a pond in a week, a lake in a month, and given the chance, an entire sea in a single prolonged season. This was Azolla's cheat code. This was how it could form a bloom so massive it changed the world. It had a biological engine that never ran out of fuel. But this incredible superpower still doesn't solve the biggest riddle of all. The bacterium gives it food, yes, but Azolla is still a freshwater fern. How did a plant that dies in saltwater manage to survive, let alone thrive, for hundreds of thousands of years on the surface of an ocean? That last question is the key to this whole mystery. How does a plant that needs fresh water take over an entire ocean? To answer that, you have to go there. You have to stand on the shores of that forgotten Arctic world. So, picture it. Stand with me on a muddy beach, somewhere in what will one day be northern Siberia. The air is thick, wet, and heavy, oppressively warm, like breathing in a global steam room. The sun never sets, circling endlessly in the pale, hazy sky of a polar summer. You look out, expecting to see the grey, choppy waves of an ocean. But there is no ocean. Not in the way we think of one. There is no blue, there are no waves. From the water's edge to the distant horizon, in every direction, there is only a single, unbroken, living carpet, a dense, tangled mat of tiny, frilly leaves, green and flushed with a deep, feverish red. It's Azolla, and it stretches on forever, an entire polar ocean, smothered. This is the scene of the crime, a world being choked by life. Now, walk to the edge, kneel down, push aside the thick, velvety layer of fern with your hand. The water beneath is dark, still, and starved of light. Dip your fingers in, touch them to your tongue. It's fresh. Not brackish, not salty. It's fresh water, as fresh as any northern lake. This is the answer to the paradox. Remember how the Arctic Ocean was almost completely landlocked? For millennia, enormous rivers had been pouring off the surrounding continents, dumping billions of tons of fresh water into this isolated basin. With no deep water connection to the global oceans, there was no circulation, no mixing. That lighter fresh water couldn't blend with the dense, salty ocean water below. Instead, it pooled on the surface. Think of it like oil and vinegar in a salad dressing. The heavy, dead, salty water formed the bottom layer, and on top of it, a vast, stable lens of fresh river water grew deeper and deeper with every century. It had become a planetary-scale Petri dish. The world's largest freshwater sea, sitting right at the top of the world. It had the 24-hour light of the polar summer. It had the suffocating warmth of the greenhouse climate. And now, it had Azolla, with its own infinite supply of fertilizer. All the conditions were met. The biological engine roared to life. But this incredible, planet-choking bloom, blooming and dying, generation after generation for nearly 1 million years, just brings us to the final, most important question of all. How does a floating fern, no matter how successful, actually cool an entire planet? How do you take a world without ice and send it into a deep freeze? So how do you take a world without ice and send it into a deep freeze? For decades, the answer to that mystery had nothing to do with life. The culprit, scientists believed, was geology, tectonics. The story went like this for millions of years. Antarctica wasn't an isolated continent. It was still connected to the tip of South America, forming a barrier that blocked water from circling the southern pole. Warm ocean currents from the tropics could flow all the way down, bathing the shores of Antarctica and keeping it temperate. It was a world without a South Pole in the way we think of one. Then, slowly, relentlessly, the continents drifted apart. A gap opened. A seaway formed between South America and Antarctica. We call it the Drake Passage. Its opening was the single most important plumbing job in the planet's recent history. It allowed the ocean currents to finally connect, forming a single, uninterrupted ring of cold water that began to circle Antarctica forever. The Antarctic Circumpolar Current. It was like building a wall of cold around the southern continent, cutting it off from the world's warmth. Antarctica became isolated, and it began to freeze solid. It became the ice-making machine that dominates our planet's climate today. It is a beautiful, elegant, and powerful theory. And it's true, it happened. There's just one massive problem with it. The timing is all wrong. The final, deep opening of the Drake Passage, the one that kicked off the formation of the great Antarctic ice sheets, happened around 34 million years ago. But the evidence is undeniable. Earth's climate began its long, steady plunge into the cold nearly 15 million years before that. The cooling started around 49 million years ago. That isn't a rounding error. It means the Drake Passage wasn't the trigger. It was an accomplice, arriving late to the scene. Something else had to have kicked it all off. And here is where our humble fern, Azolla, re-enters the story, not as a geological force, but as a biological weapon aimed at the heart of the greenhouse world. The question was never just about a plant covering an ocean. The real question is what that plant was doing, and the answer is breathtakingly simple. It was eating carbon dioxide. Every living plant does this. It's called photosynthesis. They breathe in CO2 from the atmosphere and use it to build their bodies. But Azolla wasn't just any plant. It was an exponential growth machine. On a planetary scale, for nearly 1 million years, that colossal bloom, covering the entire Arctic, was pulling CO2 out of the atmosphere at a rate the world has never seen before or since. But here is the final, crucial piece of the puzzle. When each generation of Azolla died, it didn't just rot and release its carbon back into the air. It sank. It sank through the freshwater lens and into the dead, stagnant, oxygen-starved saltwater below. With no oxygen, there was no decay. The carbon in its body was trapped, it was buried in the mud, layer by layer, year after year, forming that thick black mat. It was a one-way trip for carbon, out of the atmosphere, and into a tomb at the bottom of the sea. This wasn't a cycle, it was a drawdown, a planetary-scale carbon sequestration event, run by a single tiny fern. The Azolla event stripped the Earth's heat-trapping blanket away, thread by thread, and buried it forever. The timing fits perfectly, the mechanism is undeniable. The old mystery of the cooling Earth finally had its missing trigger. And so the great climate mystery was solved. It wasn't a continent moving, it wasn't a volcano erupting, it was a plant, a tiny, humble fern that pulled off a planetary-scale coup. But this raises a question of scale, a question that feels rooted in common sense. How can one plant, in one isolated ocean at the top of the world, change the climate of the entire planet? How does a bloom in the Arctic make an ice sheet form in Antarctica? To understand this, you have to remember that the Earth's atmosphere isn't a collection of separate local air pockets. It's one vast, interconnected, and constantly mixing ocean of air. When you take carbon dioxide out of the air in the Arctic, you are taking it out of the air in the Amazon. When you sequester it at the North Pole, you lower the concentration over the equator. Think of it like adding a single, powerful filter to a giant swimming pool. It doesn't matter where you put the filter, sooner or later, all the water will pass through it. The entire pool gets cleaner. This is what Azolla did. For nearly 1 million years, this massive biological pump, powered by 24-hour sunlight and an endless supply of self-made fertilizer, was relentlessly filtering the Earth's atmosphere. The effect wasn't instantaneous. It was a slow, inexorable, global drawdown. Every year, a little more CO2 was buried than the planet's volcanoes could put back. Thread by thread, the Earth's thick, heat-trapping blanket was being unraveled and tucked away at the bottom of the sea. The thermostat was turning down, millennia by millennia, degree by degree. This was the first domino. The Azolla event didn't create the Antarctic ice sheets directly, but it primed the pump. It cooled the planet just enough so that when the Drake Passage finally did open millions of years later, the world was already teetering on the edge of a deep freeze. Azolla pushed it over the edge. It set in motion the chain of events that would define our modern world, our world of ice. So the great cooling had begun. But what did that new, colder world actually look like? What happens when a planet that has known only warmth for 100 million years finally learns the meaning of ice? So, what happens when a planet that has known only warmth for 100 million years finally learns the meaning of ice? The change isn't sudden. There is no single, catastrophic winter. Instead, the Earth gets a new rhythm, a new pulse. For the first time since the dinosaurs, the poles experience true seasonality. The endless swampy summer of the hothouse Arctic gives way to a cycle. In the winters, the surface of the polar sea, once smothered in green fern, begins to freeze. A thin, fragile skin of sea ice forms, something the planet hasn't seen at its northern pole for an eternity. In the summer, it melts away. Winter is born at the top of the world, and with it, the rules of life begin to change. For the creatures of the greenhouse, the crocodiles, and palm trees that had thrived in the polar warmth, this was the beginning of the end. Their world was shrinking, the global steam room was slowly venting its heat into space. But for another group of animals, a group that had lived in the shadows for 100 million years, this was not a crisis. It was an opportunity. This was the dawn of the age of mammals. Warm-blooded, covered in insulating fur, and adaptable, mammals were perfectly pre-built for a cooler world. While the old order of hothouse life retreated, mammals exploded into the newly opened ecological spaces. They grew larger, they diversified into an incredible array of forms, from the ancestors of whales returning to the sea, to the first horse-like creatures galloping across the cooling plains, to the first primates learning to navigate the changing forests. This is the world that began to shape our own deepest ancestors. The slow, inexorable cooling, triggered by a tiny fern in a forgotten ocean, set the stage, creating the environmental pressures that would favor a new kind of animal, one that was clever, social, and able to adapt to a world that was becoming more challenging and more dynamic. With every passing millennium, The Azolla event had thrown the first switch. The planet was now on a one-way trip toward a deep freeze. But it wasn't there yet. The thermostat was turned down, but the final catastrophic plunge into our modern icehouse world required one last massive geological event. The world was balanced on a knife's edge, waiting for the final domino to fall. It's a scale that is almost impossible to hold in your head. The Azolla event didn't last for a season, or a century, or even a millennium. This incredible planet-altering process ran continuously for somewhere around 800,000 years. To put that in perspective, our species, Homo sapiens, has only existed for about 300,000 years. This single fern bloom lasted more than twice as long as our entire history, generation after generation after generation of fern, blooming, dying, and sinking, in an unbroken cycle that outlasted mountains rising and falling. So, here is the question that defines the entire event. What does that actually do to a planet? What happens when you run a biological carbon pump at full throttle for nearly 1 million years? The numbers are staggering. Over the course of the event, this one tiny plant drew down so much carbon dioxide that it slashed the planet's atmospheric concentration, potentially by as much as half. We're talking about a drop from over 1,000 parts per million, down to levels the planet hadn't seen in tens of millions of years. Think of it this way. All of our modern industrial activity, every car, every factory, every power plant, pumps billions of tons of carbon into the atmosphere each year. Now imagine a natural process that did the reverse, at a relentless geological scale for 800,000 years straight. It was the largest carbon capture and storage project in Earth's history, run by a microscopic fern. This was the push the Earth's climate needed. It sent the global system past a critical tipping point. The hothouse world was now fundamentally broken. The thermostat wasn't just turned down. The wiring had been ripped out. The planet was now committed irrevocably to a long-term cooling trend. The great deep freeze had begun, but this was only the first act. Azolla had loaded the gun. The planet was now colder, balanced on a knife's edge. Millions of years would pass before geology stepped in to finally pull the trigger. It's a spectacular story. A planet-choking bloom of a single, humble fern, pulling enough carbon out of the air to break a 50-million-year-long heat wave. It's dramatic, it's epic, and it makes for a great theory. But in science, an epic theory needs epic, independent proof. A good detective doesn't just trust the first clue they find. They have to corroborate it. They have to find completely separate evidence that points to the same conclusion. How can we be absolutely sure that a fern bloom at the North Pole really cooled the entire planet? How do we prove this wasn't just some bizarre local Arctic phenomenon? To do that, we need a global thermometer, a way to read the Earth's temperature, not just in one place, but everywhere, all at once. 49 million years ago, and believe it or not, we have one. The answer lies, once again, at the bottom of the ocean, not just in the Arctic, but in every ocean on Earth. Buried in the sediment are the fossilized remains of countless trillions of microscopic single-celled organisms called foraminifera. Forams. They look like tiny, intricate seashells, and for geologists, they are one of the most powerful tools ever discovered. Think of each one as a tiny chemical time capsule. As a foram grows, it builds its shell out of calcium carbonate, using atoms from the seawater around it, including oxygen atoms. But not all oxygen atoms are the same. There's a common, lighter version, oxygen-16, and a rarer, heavier version, oxygen-18. Here's the trick. The ratio of these two oxygen isotopes in the ocean changes with global temperature. When the planet is colder, more of the lighter oxygen-16 gets locked away in massive continental ice sheets, leaving the oceans enriched with the heavier oxygen-18. So when a foram builds its shell in cold water, it automatically incorporates more of that heavy oxygen. It's a direct chemical record of how cold the world was when that creature was alive. More heavy oxygen in the shell means a colder planet. It's that simple. So scientists went to the archives. They examined deep-sea sediment cores drilled from the Atlantic, the Pacific, the Indian Ocean, from all over the world. They meticulously separated out the tiny foram shells from layer after layer. and they analyzed the oxygen isotopes in them. They were building a continuous global temperature record spanning millions of years. And as they looked at the data for the period around 49 million years ago, they saw it, clear as day, a sharp, distinct, and global shift toward colder temperatures. It wasn't a local signal, it was everywhere. It was the signature of a planet beginning to cool. And here is the final, case-closing piece of evidence, the linchpin of the entire story. When did that worldwide temperature drop begin? When did this global cooling event, recorded in the shells of dead sea creatures from every corner of the Earth, actually start? It started at precisely the same moment in geological time that the first layer of the Azolla black mat was laid down at the bottom of the Arctic Ocean. The timing wasn't just close, it was perfect. The global thermometer confirmed the story told by the Arctic fern. The fingerprints found at the global crime scene matched the suspect found at the North Pole. The Azolla event wasn't just a regional curiosity. It was the trigger. It was the moment our world began its long, unstoppable slide into the icehouse. The evidence was in, the case was closed. The Azolla event was not a theory. It was a fact, written in the stone and mud of the planet itself. The verdict had been delivered, and now the sentence would be carried out. Not over a lifetime, but over millions of years. The world did not freeze overnight. It was a slow, majestic, and brutal decline. A long, drawn-out autumn that lasted for an eternity. The hothouse Earth, which had hummed along for 100 million years, was finally losing its heat. Azolla had permanently propped open the door, and the warmth was bleeding out into the cold of space, year by year, millennium by millennium. And with the cooling, the great dying began, not with an asteroid, not with a volcanic firestorm, but with a long, slow chill. For the children of the greenhouse world, it was the end of everything. The polar crocodiles, those stunning symbols of a world so warm it defied imagination, found their swampy rivers growing numbingly cold. Their food disappeared. The endless summer of their ancestors was replaced by a new hostile season called winter. Generation by generation, their world shrank. They were refugees on their own planet, chased south by a cold they could neither fight nor comprehend. And then they were gone. An Earth warm enough for crocodiles at the North Pole had vanished forever. In its place, something new appeared, something alien, a substance the planet had not seen on a grand scale for tens of millions of years. Over the isolated continent of Antarctica, the cooling winters began to leave their mark. At first it was just frost, then snow that survived the summer. That snow, falling season after season, and never melting, began to compress under its own immense weight. It was no longer just snow, it became something harder, denser, bluer. Ice. A word a planet had all but forgotten, and now it was the most important word in the world. For the first time since the age of the dinosaurs, a permanent ice cap began to grow, a glittering white sheet spreading across the southern pole. The hothouse was fundamentally broken. The icehouse had begun. This was the true dawn of our modern climate, the beginning of a new regime, defined not by stifling warmth, but by the relentless, grinding power of glaciers. The world Azolla had made was colder, harsher, and far more volatile. But this was only the first chapter of the Great Deep Freeze. The world was cold now. What would it take to make it truly frozen? And so the old world died, not in fire, but in frost. The planet crossed a threshold from which there was no return. The hothouse life that had dominated the Earth for 100 million years. The crocodiles basking at the poles. The palm trees swaying in a world without winter was now on borrowed time. Their planet was gone. It had been replaced by a world that was learning a new cold language, whispered first as frost, and then proclaimed in sheets of ice. But to ask what it would take to make the world truly frozen is in a way to miss the most profound and unsettling lesson of the entire story. The next geological steps in the Great Cooling are their own epic tale of continents drifting and mountains rising. Yet they are just accomplices to the crime that had already been committed. The most important domino had already fallen, and it wasn't pushed by the blind, slow-grinding power of tectonics. It was pushed by life. This is the part that stops you cold. The entire story of the Azolla event is a stunning 49-million-year-old testament to a fact that is both terrifying and awesome in its implications. Life is not a passenger on this planet, decorating a dead rock. Life is a planet-scale chemical force, capable of grabbing the wheel and steering the entire system. For nearly 1 million years, a single, humble fern hijacked the Earth's climate. It did what we are now doing, but in reverse. It found the planet's master thermostat, and deliberately, relentlessly, turned it all the way down. The mystery we started with, what could possibly flip a switch on a global scale, has its answer. It wasn't a what, it was a who. From the first strange clue, in a smear of black mud, to the audacious mission to drill at the North Pole, to the final confirmation written in the shells of tiny sea creatures across the globe, the evidence has been pointing to one culprit. A plant that for a moment in deep time became a geological force, a plant that ended a world of warmth and ushered in our own age of ice, leaving its tombstone at the bottom of the Arctic Ocean as the final, stunning proof that on this planet, the smallest of things can change everything.